We're going to cover real quick binary coded decimal. And the binary coded decimal system really requires us to be fairly proficient with binary or base 2 and decimal system or our base 10 systems to be fairly proficient. We understand that with binary there's a lot of applications, especially within the PLC ranks. PLC math instruction executes math operation as binary or base 2. More particular, when you're looking at conversion instruction in a PLC, it's using BCD or the binary coded decimal system and converts that over to an integer or vice versa, an integer over to BCD. Where conversion instruction may not be as prevalent as it had once been, especially with the onset of HMI and other things. For older systems and in some rare applications, we still want to have some base proficiency with it. So, as mentioned, we need to understand a little bit about binary, or base 2, and a little bit about decimal, our base 10 system. So, let's remember and recall what we know about each of those real quick. Our decimal system, which we also call base 10, is unique in the fact of its placeholders, right, or its value system. And we know that it has a ones place, a tens, a hundreds, a thousands, 10,000s, 100,000s, and so on. And this is how we would construct a number on the base 10 system. Also keeping in mind that the digits that we use with base 10 will span anywhere from 0 to 9. So any number 0 to 9 can occupy within these value systems for us to construct any number from 0 to infinity, if you will. Alright. In contrast, our binary or base 2 system, the digits we use is going to be zeros and ones. And that power table is constructed again off of bases of 2, not bases of 10. Right? So we construct this. We start off with a 1, go 2, 4, 8. 16, 32, 64, 128, and so on. And again, we can assign a 1 or a 0 throughout here to construct a very similar digit to decimal. Alright. So with this basic understanding of the decimal and binary system, we should be fairly well equipped to look at the BCD, binary coded decimal system. What makes it unique is that it will use the first 4 bits in binary to represent any of the digits 0 through 9 in decimal form. So I'll construct a little chart real quick that will help us pull this together. Alright, so what we're going to look at on the front end is the top being our decimal, And keep in mind, this could certainly stretch and be much longer, but we're going to be looking at the decimal side up here, our integer values, and then we're going to be looking at the BCD on the bottom. What I'm about to do right now is really what makes BCD unique. We had talked about BCD representing each decimal digit, each decimal number that would normally occupy within either the ones, the tens, the hundreds, and so on, is going to represent those not just in a linear path like as with typical binary, but as 4-bit digits to represent that actual digit. So what we'll actually do is be segmenting each one of these individually. And for each one of these columns, it's going to carry that same binary outfit, the 4-bit, just the first 4 bits. So 1, 2, 4, and 8. So what we have here is now the means and ability to represent each digit for a decimal number with the first 4 bits of binary. So let's throw out just a quick example. Let's say fairly generic. Let's say 27. Right? How would we represent that? So what we want to do is, we're not trying to go through and represent it the way we have in times past, where we normally in binary say, well, let's represent 27. And we might say, okay, we'll go with 16. Now we need 9, 0, 0, 1. That equals 27. Not quite. All we need to do is for whatever the placeholder, this value, we need to represent just that digit. So for example, we would say 0, 1, 2, 3. And then for this next set of 8 bits, alright, so we start over, say 0, 0, 1, 0. So the way this would read in BCD is that 27 equals 0, 0, 1, 0. Give ourselves a little bit of a space, 0, 0, excuse me, and 0, 1, 2, 3. Because this is your 2 and this is your 7. Alright. We'll do another quick example. Let's kind of move it over into not just the, we know again decimal form, we got the ones, we've got the tens, the hundreds, etc. as we move through. Let's give ourselves, say, 539. The way we're going to represent this is, we're just going to craft with the first 4 bits is a 9, 0, 0, 1. We need a 3, 0, 0. And 2 and a 1, 0, 1, 0, 1. So we would then say that 539 is equal to 0, 1, 0, 1. Okay? So this is the BCD equivalent, because this equals 5, 3, and 9. We'll do one more just as a quick example. And so this is a fairly elaborate drawing. You certainly don't have to go through and draw all this out, because once you understand the basic layout of binary, you can pretty much craft this any way that you need. Very minimal, with very minimal effort. Alright, we'll take this one just one step further, and let's go 7. We'll say 3, 4, and 1. 7,341 in decimal. How do we convert that to BCD? We'll start in the ones column. Let's go ahead and go over here. 0, 0, 0, 1. Let's go to the tens. 0, 1, 0, 0. Let's craft 3. In the hundreds column, 0, 0, 1, 1. And then in the thousands column, we're going to have 0, 1, 2, 3. we got 7, 3, 4, and 1. So 7,341. And that's our BCD equivalent.